Class 12th Chemistry, Haloalkanes and Haloarenes, and in this video we will discuss about mechanism of nucleophilic substitution reactions. This is the representation of nucleophilic substitution reaction. Alkyl halide react with the nucleophile, and this nucleophile substitute this halogen and we will get the product. This reaction has been found to be proceed by two different mechanisms, SN1 and SN2. Now what are the meaning of these SN1 and SN2? S stand for substitution, N for nucleophilic, and this is 1 for unimolecular. We can say unimolecular nucleophilic substitution. In this case, S for substitution, N for nucleophilic, and this 2 for bimolecular nucleophilic substitution reaction, SN1 and SN2. First come to SN2 reaction. It occurs in single step. It involves formation of transition state. It occurs with inversion of configuration. The reaction between CH3Cl and hydroxide ion to yield methanol and chloride ion follows as second order kinetics. That is, the rate depends upon the concentration of both the reactants, and this can be written like this. This is CH3Cl, this is nucleophile hydroxide and attacks on this. This is transition state. In this transition state, this OH is approaching to this carbon and this Cl is detaching from this carbon. Okay, and finally we will get this alcohol and chloride ion. Now what is the meaning of this inversion of configuration? Just see the attachment of halogen in this and compare the attachment of nucleophile in this. Okay, this is inversion. This can be compared. This is the umbrella, and when there is a wind is there, then this umbrella is inverted like this. This is called inversion. Okay. Now what is the meaning of configuration? Spatial means space. Spatial arrangement of atoms or groups around carbon is called its configuration. There are two structures of the same compound. You can say this is the compound A and its mirror image is compound B, but both are different, not both are same. Configuration of carbon in structure A is mirror image of the configuration of carbon in structure B, and we can say actually this is called inverted structure of this one, inverted configuration of A. Okay, this SN2 can also be represented like this diagram. This is CH3Cl and this is approaching nucleophile. Okay, and actually this is NaOH. This is Na and this is OH. This OH is approaching to this carbon. This is transition state and this is our final product. Bond between the incoming nucleophile and the carbon atom starts forming. The bond between carbon atom and leaving group weakens. You can see this is bond forming and this is bond weakening. In the transition state, all the three carbon hydrogen bonds are in the same plane. You can see this. This is carbon attached with these three hydrogen atoms, and the attacking and leaving nucleophiles are partially attached to the carbon. These dotted bonds represent the partial attachment with this carbon. Thus, in transition state, carbon is simultaneously bonded to 5 atoms. Such structures are unstable and cannot be isolated. Now, order of reactivity. Primary halides are most reactive towards SN2, secondary halides are less reactive, and tertiary halides are least reactive. Now, what is the reason? The presence of bulky substituents on or near the carbon atom have steric hindrance. Methyl halides react most rapidly in SN2 reactions because there are only 3 small hydrogen atoms. Tertiary halides are the least reactive because bulky groups hinder the approaching nucleophiles. You can see this diagram. This is methyl halide. Okay, nucleophile can approach easily because only 3 hydrogen atoms are attached to this carbon. This is primary halide. In this case, one of the hydrogen atom from this methyl is replaced by CH3. Now again you can say this Nu, that is nucleophile, attacking nucleophile will feel steric hindrance from this methyl group. In case of isopropyl, that is secondary halide, now 2 methyl groups are there, one and this is another. This is steric hindrance increases. Now in case of tertiary halide, okay, this is 3 methyl groups, 1, 2 and 3. Now you can see that is approach of nucleophile to this carbon becomes difficult. Okay, and this in bracket, this is the relative rate of SN2 reaction is given, that is this is 30, this is 1, 0.02 and this is 0. Now you can clearly see that is methyl halides are most reactive towards SN2, then primary halide, secondary halide, and reactivity of tertiary halide is least towards SN2 reaction. Now SN1 Substitution, nucleophilic, unimolecular. SN1 reactions are generally carried out in polar protic solvent. Now what is the meaning of this polar protic solvent? Protic means which can give proton easily, okay, like water, alcohol, acetic acid, etc. The reaction between tertiary butyl bromide and hydroxide ion yield tertiary butyl alcohol and follows the first order kinetics, that is the rate of reaction depends upon the concentration of only one reactant, which is tertiary butyl bromide. This is the overall representation of the reaction. This is tertiary butyl bromide and this is the IUPAC name of this compound, 2-bromo 2-methyl propane. This is nucleophile taking on this, and this Br is substituted by this OH and we will get 2-methyl propane 2-ol. SN1 occurs in 2 steps. In step 1, the polarized carbon-bromine bond undergoes slow cleavage to produce a carbocation and a bromide ion. You can see this is the step 1. Okay, this bond is polarized. Okay, undergo cleavage and form this is carbocation and this is bromide ion. Now in the second step, carbocation thus formed is then attacked by nucleophile in step 2 to complete the substitution reaction. This is carbocation is attacked by the nucleophile in the second step and we will get the final product. Okay, so simply remember SN1 taking place in 2 steps. In this carbocation is formed, SN2 taking place in the 1 step and transition state is formed in SN2. Okay, primary alkyl halides are more reactive in SN2 while SN1 tertiary alkyl halides are more reactive. Now what is the reason? Step 1 is the slowest and reversible. Okay, and in that step formation of carbocation takes place. Since the rate of reaction depends upon the slowest step according to the kinetics, the rate of reaction depends only on the concentration of alkyl halide and not on the concentration of hydroxide ion. And in the slowest step, only one molecule is there. That's why this is unimolecular reaction. Further, greater the stability of carbocation, greater will be its ease of formation from alkyl halide and faster will be the rate of reaction. And we know that is tertiary carbocation is most stable. That's why tertiary reactivity of the tertiary halide is most towards SN1 reaction. Then for secondary, this is less, and for primary, this is least. From this, you can summarize tertiary halide, secondary halide, primary halide, and CH3X. This is the increasing order of reactivity of SN2 reaction. Okay, that is tertiary halide is least reactive, and primary halide or methyl halide most reactive. For SN1, this is the order is reverse. Tertiary halides are most reactive and primary halides are least reactive. Okay. And on the basis of that is stability of carbocation, we can say that is allylic and benzylic halides show high reactivity towards the SN1 reaction because the carbocation formed gets stabilized through resonance. Now see, this is allylic bromide, CH2 double bond CH single bond CH2 Br. In the first step, this allylic carbocation is formed, and this allylic carbocation is resonance stabilized. These are the two resonatic structure of this. Okay, this pi bond, electron of pi bond will shift to here, and positive charge develop on this carbon. In the same way, this is benzylic bromide. In the first step, this benzylic carbocation is formed, and this benzylic carbocation is more stable due to resonance. You can see again, these are the resonatic structure. You must be able to write these resonatic structure. Okay. Now see, example 10.6. In the following pairs of halogen compounds, which would undergo SN2 reaction faster? Now again, you have to know SN2 means single step. Single step means the alkyl halide which has least steric hindrance. Okay. Now you can compare this and this, in which steric hindrance is least. In this case, this here is present on this carbon, and this carbon is attached with the only two hydrogen atoms. Okay, while this here is attached to this carbon, and this carbon attached with this another carbon, and this is another carbon. That's why in this case steric hindrance is least. That's why it is a primary halide and therefore undergoes SN2 reaction faster. Now in this pair, in this case this I is there and this is Cl is there. Size of this iodide ion is greater. Okay, that's why carbon iodine bond is weaker. That's why its answer is this. This will undergo fast in SN2 reaction. As iodine is a better living group because of its large size, it will be released at a faster rate in the presence of incoming nucleophile. Now see, there is one more example. Predict the order of reactivity of the following compounds is SN1 and SN2. First one is the 4 isomeric bromobutanes. First of all, you must be able to write the structure of these isomeric bromobutanes and classify them as primary, secondary, tertiary. Okay, now you can see these are the structures of these 4 isomeric bromobutanes. This is primary, this is secondary. Okay, and these two structures are obtained from the normal butane. Okay, and these two structures are obtained from the isobutane. This is again primary and this is tertiary. Now in case of SN1 again, SN1 means occur in the two step means stability of carbocation is considered. That's why tertiary carbocation most reactive towards SN1. Okay, then secondary, this one is the secondary, and primary we are having two, this one and this one. Out of these two, which will form more stable carbocation? We can say this, definitely this one form more stable carbocation. That's why this, and least one is this. Okay, and reverse for SN2, okay, only just change the sign this. Okay, it means this is primary is the most reactive towards SN2 and tertiary is the least reactive towards SN2. One more example. This is C6H5CH2Br, C6H5CH, C6H5Br, C6H5CH, CH3Br, C6H5C, CH3, C6H5Br. Dear student, This is little difficult to find out which one is primary, secondary and tertiary from structures represented like this. That's why write these structures in this form. Okay, now this is primary, you can easily see. Now in this case, this CH, that is this carbon attached with C6H5, another molecule of C6H5 and Br. Now you can say this carbon is a secondary. That's why this is secondary halide. Now in this case, this carbon attached with the C6H5, CH3 and Br. This is again secondary. Now in this case, this carbon is attached with the 3 alkyl and aryl groups, like this is C6H5, this is one, then this is CH3, this one, this is C6H5, this, and this is Br, and this is tertiary. Now I think it is easy for you to write the order. For SN1, again remember, SN1 means occur in 2 steps. Stability of carbocation is considered, that is tertiary carbocations are most active towards, tertiary alkyl halides are most active towards SN1 reaction. That's why this tertiary, this one is the most reactive. Okay, then there are 2 secondary halides are there, which will be most reactive. Now in this case, 2 benzene rings are there. In this case, 1 benzene and 1 alkyl group is there. When 2 benzene rings are there, due to resonance, that carbocation is more stable. That's why this is placed here. Then this one, and least one is this primary. Is it clear? And for SN2, just reverse the order. This one, now we can say this is primary is the most active and this tertiary is the least active. Okay student, thank you.